Hi, my dear student friends. Today we are going to discuss about the dynamics of 2 degree of freedom manipulators. How the modeling of a robo arm, 2 degree of freedom arm. We are going to discuss two types of arm using the Lagrangian Euler dynamics. Okay, Lagrangian Euler dynamics. So we already discussed about the uh, Lagrangian equation L equal to kinetic energy minus potential energy. Okay. So what Lagrangian Euler dynamics for the control system design purpose, it is to have a mathematical model that reveals the dynamical behavior of the system. Therefore, today we are going to derive the dynamic equations of motion of a two types of robo manipulator. Our approach is to derive the kinetic potential energy of the manipulator and then use Lagrange's equation of the motion to model to derive the dynamic equations, right? So what are the basics we should know before going for the dynamic analysis? We should know three things basically: force, inertia, and energy. Okay, and energy and energy. So these three are very important to know to derive the dynamic model of the manipulators. Okay. So then the centripetal force, the force, basically the force, main force is the centripetal force. Centripetal force. Centripetal force of a mass on orbiting a point with a radius at a radius of r. Okay, this is nothing but centripetal force of a mass m. Okay, m orbiting. Okay, orbiting a point. Orbiting a point at a radius. At a radius r and the angular velocity omega, right? Angular velocity omega is given by f equal to so f centripetal equal to mass velocity, linear velocity by r, mv square by r, that is m omega square r or m theta dot square r. Okay, so the linear velocity, the relation between the linear velocity and the angular velocity is the linear velocity equal to, that is v equal to omega r, the relation between linear velocity and the angular velocity. Clear? So what actually happens in the centripetal force? Just imagine yourself, say, okay, say, so rotating, this is the angle theta. Say consider this is angle theta, this is the radius r. At this point it is orbiting. Okay, so this is the angular velocity, this is the centripetal force. Okay, this is called centripetal force. The mass is the end, okay, the joint mass. Okay, so this is given by this is centripetal force. Okay, this is centripetal force representation. Okay, then just imagine a sphere. Okay, a sphere is rotating like Earth. Okay, like Earth, it's rotating about its center with an angular velocity omega. Okay, so the Coriolis force, the Coriolis force is on a body of mass m. Coriolis force of a body mass m with the mass m moving with a velocity. Okay, moving with a velocity v on the surface of the sphere. Sphere is given by f. Okay, f Coriolis equal to 2m omega okay into v, 2m omega into v. Clear? So using right-handed screw rule, if the fingers rotate with the omega, okay, omega or omega naught, we consider omega naught, okay, with the velocity omega naught. Say, okay, omega naught, right? So using right-handed screw, we can explain the rotate omega naught and v, the thumb points in the direction of omega naught into v. Okay, omega naught into v, thumb points. So omega naught into v is considered, okay, this is we see the velocity v omega naught 2m omega naught it's okay. Using the right-handed screw rule, if the fingers omega naught, foot fingers rotate, okay, if the fingers rotate omega naught and into omega naught into v, okay, the thumb points in the direction of omega naught into v. You see that from this figure, the Coriolis force acts to deflect m to the right direction. Okay, so the Coriolis force, how Coriolis force affect? Okay, so the Coriolis force, this omega naught, say omega naught, see this figure. So this is theta. This is the R. This is omega naught. Say this is right angle. This is right angle to the omega naught. Okay, so from here we can have a similar right angle, similar right angle. So this is say consider this is 5. Okay, this is 5. So these are similar triangles. So theta, not 5, theta. So this is theta. This is small r. Sorry, v. This is m mass. This mass is rotating with the velocity v. With the velocity v. This is radius. This is called a Coriolis force. This is called Coriolis force. Okay, so theta is rotating in right hand side, right hand side. So this is Coriolis force. Okay, Coriolis. Coriolis force. So the kinetic energy equal to half mv square. Okay, so the rotating kinetic energy, the rotating kinetic energy of a mass m. Okay, in this figure, you see this figure, rotating mass in this figure. K kinetic energy rotating equal to half I omega square. Okay, I is moment of inertia, right? So what is moment of inertia? Then moment of inertia. Inertia I equal to integral of rho r into r square dr. Okay, what is rho r? Rho r is mass distribution. Rho r is mass distribution. Mass distribution. Mass distribution at radius r in a volume. In a volume. Okay, in a volume. In simple case, shown in mass at a point. Okay, mass at a point. So I equal to, in simple force, what is I moment of inertia? I equal to m r square. Okay, so therefore kinetic energy rotating kinetic energy becomes half m r square theta dot square theta dot square. Okay, the potential energy of a moving mass m, moving mass m, moving with a velocity v is given by p equal to mass momentum. Okay, this is momentum. Sorry, potential energy of mass. Sorry. So the potential energy, the potential energy of a mass m at a height, okay, at a height h is in a gravitational, okay, in a gravitational force or gravitational field with constant force or gravitational with constant g equal to what is p? Sorry, potential energy equal to mgh. Similarly, the angular momentum of a mass moving with velocity v. So angular momentum equal to p angular. Angular momentum equal to r into p. Okay. What is linear momentum? In simply, momentum of a mass m moving with velocity v equal to velocity v is p equal to mv. The relation between the p angular and the linear momentum is r into p, right? So next is torque or moment. Torque or moment of a force, F with respect to the same origin. Is given by n equal to r into force. So radius into force. Clear? So the Lagrangian solution, Lagrange's equation of motion. We already studied the Lagrange's equation of motion for a conservative system, conservative system, system is given by the relation d by dt of dou L by dou Q dot minus dou L by dou Q equal to tau. Okay, where Q is the n vector of generalized coefficient. Q is n vector, n vector of generalized coordinates. Okay, so generalized coordinates Q. Okay, so QI. So generalized coordinate is QI. Q is n vector of generalized coordinate QI, and tau is the n vector of generalized forces. N vector of same generalized forces tau I. So the Lagrangian is the difference. The Lagrangian is the difference. Okay, difference between kinetic energy. This difference between kinetic energy and potential energy. Okay, that is L equal to K minus P. So L equal to K minus P. This is Lagrangian equation. Okay, so using this we can obtain. First, we are going to obtain, or we are going to derive the dynamics of two-link polar arm. Okay, two-link polar arm. So first, we are going to see dynamics of two-link polar arm. First, we see the dynamics of a two-link polar arm, polar arm, polar arm. So the dynamics of polar arm is given by, what is polar arm? So polar arm has say one base, one link L, then this arm is angular, so polar angular rotation. So this is the end of the robo arm whose mass is m. So this gravitational pull is g. This has a radius r. Clear? So the dynamics of polar arm for the prismatic or revolute or planar. Okay, planar is given already discussed planar. To determine the dynamics where the joint variable and joint velocities are. Okay, for this the joint q equal to theta r. Then q dot equal to theta dot r dot. So this is the joint variable and joint velocity. This is joint variable. This is joint velocity. Joint variable. This is joint velocity. Okay. So the corresponding force vector, whose they say this is equal to equation number 1. The corresponding force vector tau equal to NF. NF. Clear? So this is the corresponding force vector. With N is a torque and F is a force. The torque N and force F may be provided by either motor or hydraulic actuators. So this N and F, okay, are provided by. So this which provides N and F, either motors or hydraulic actuators. Hydraulic actuators. Clear? Hydraulic actuators. To determine the arm dynamics, we must know we must now compute the quantities required to the variables required for Lagrangian equation. Okay, what are the quantity? First part is first part A. So A part we have to compute kinetic energy and potential energy. Okay, so the total kinetic energy due to the angular motion theta dot, okay, theta and the theta dot and the linear motion tau dot, right? So the kinetic energy, the total kinetic energy due to the angular motion, angular velocity, okay, angular motion, angular motion theta dot and tau dot. Okay, tau dot is given by kinetic energy K. Total kinetic energy equal to half mr squares. Sorry, I missed that. This not tau dot, the theta dot and the r dot. Okay, sorry, theta dot and r dot. R. Okay, this vector. Okay, so mr square theta dot square, mr square theta dot square plus half mr dot square. Okay, so this is the total kinetic energy. So next is what is potential energy? Okay, potential energy. P equal to, for this this is the polar arm. Okay, polar arm. This figure shows polar arm. So from this polar arm, what is the kinetic energy? Sorry, potential energy. P equal to mgr mgr sin theta. Whereas when a planar have h at a height h, then p equal to mgh. Whereas here it is making the angular rotation. So potential energy is mgr sin theta. Okay. So this say consider this is equation number 3. This is equation number 4. Say this is equation number 2. Okay, so next part is B. So first step A, second step is B. B is Lagrangian equation. What is Lagrangian equation? L equal to, so using Lagrangian equation, what is kinetic energy minus potential energy? So L equal to, what is kinetic energy of mr square theta dot square plus of mr dot square minus mgr sin theta. Say equation number 5. Okay. So now we know the Lagrangian equation equal to, so dou d by dt of dou L by dou Q dot minus dou L by dou Q equal to tau. So using this relation, we obtain dou L by dou Q dot equal to dou Q by dou Q dot equal to dou L by dou theta dot dou L by dou R dot. Okay, what is dou L by dou theta dot? So differentiate this equation. Differentiate equation 5 with respect to Q dot, right? So if you differentiate it, so you will be getting mr square theta dot. Here simply mr dot. Dou L by dou R dot, dou L by dou theta dot. So next d by dt of dou L by dou Q dot. So you just differentiate this with respect to Q dot, right? T, with respect to T, we will be getting mr square theta dot, theta double dot, okay? Theta double dot plus 2mr r dot theta dot. Similarly, here m r double dot here. So then dou L by dou Q, differentiate the Lagrangian equation with respect to Q, we will be getting minus mg r cos theta. Similarly, mr theta dot square minus mg sin theta. So we have equation, this say equation 6, equation 7, equation 8. Okay, equation 8. So what we have to do, the arm dynamic equations are the arm dynamic equations are, okay, what are the dynamic equations? mr square theta double dot plus 2m r dot theta dot plus mg r cos theta equal to n. Cos theta equal to n. So this is equation number 9. Next equation is mr square minus mr theta dot square theta square. Sorry. Theta square plus mg sin theta. This is force. This is n. This is force. Okay. So n and force. These two are. This is a set of coupled nonlinear differential equations. Okay. Coupled set of nonlinear differential equations which describe the motion q of t. Motion q of t equal to theta of t r of t, okay, transpose. So these equations are nothing but this is taken from here, okay, mr square theta double dot mr double dot here mr double dot then mr square minus mr square theta square plus mg sin theta, okay. So from this relation only we obtained here. So this set of equation, the first equation, okay, equal to this. Understand? So the dynamics, the two dynamic equations, couple of nonlinear differential equations for the given control input force. So given torque given by the control input, the control torque, control input torque, control input. Say this is input n of t and force f of t, force f of t, okay, force f of t. So now in our discussion, this force and inertias are easy to identify in the dynamic equations, right? The first term in each equations are acceleration term involving masses and the first term in the dynamic relation. First term in terms in each equation or acceleration terms involving masses and inertias, involving masses and inertias. Okay, the dynamic equation first term, okay, the first term is acceleration, the second term is Coriolis term, okay, Coriolis term. This is the standard, okay, second term. The third term is normally gravity term. So Coriolis acceleration, first term in the dynamic equation is, first term is acceleration term, second one is Coriolis term, then gravity term. So these three are the important. So in the third part, see the manipulator, first we compute kinetic energy, then we compute the Lagrangian equation parameters. The third one is manipulator dynamics, manipulator dynamics. Okay, manipulated dynamics. Using these vectors, the arm equations may be written in the convenient form, like a matrix form. Okay, so what is the matrix form? So the convenient form for manipulated dynamics is mr square 0 0 m. Okay, then theta double dot r double dot plus 2 m r dot r theta dot minus m r theta dot square plus mg r cos theta mg sin theta mg sin theta mg sin theta equal to this equal to nf. Say this is equation number 11. Consider. So just we are rewriting these equations, okay, in this format. So the 9 and 10, equation 9 and 10 are written in the convenient form for our convenience. Understand? So this symbolize this one is m of q. The first term related to acceleration, second order term. So m of q into q double dot plus second term. This is acceleration term. Second term is Coriolis term. So this is Coriolis vector. Okay. So Coriolis vector. This is Coriolis vector. So this is v of q comma q dot plus gravity term g of q equal to tau. This is equation number 12. So this is the representation of manipulated dynamics. Okay. So it is note that the inertia matrix m of q is a function of q, that is theta and r. The Coriolis vector function of q. Okay, q double dot. This is m of q is the function of q double dot, right? That is theta and r. Theta function of theta and r. Okay, so this is function of theta and r. Understand? Similarly, the Coriolis centripetal force. This is the Coriolis centripetal force is a function of q and q dot. This is a Coriolis term. So the g gravity term is a function of q. Clear? So this is all the manipulated dynamic equation for polar. Okay, polar robo. 2 degree of freedom, polar arm robo. Understand? So this is the dynamic equation of polar arm. Understand? Next we see. Now we see how to derive the dynamics of two-link planar elbow arm. Okay, two-link planar elbow, 2 degree of freedom. Okay, so the dynamics of 2 degree of freedom RR robo. Okay, RR robo, planar robo, 2 degree of freedom planar robo. So the kinematics of RR robo, you know that the component of a 2 degree of freedom robo so the link masses are So this is angle theta 1. This is angle theta 2. Clear? So this is link mass m1. Here link mass m2. This say a1, link length a1, link length a2, or l1 l2, whatever may be you can consider. So the r, rotation r is in this direction. Clear? The planar direction. Okay. So the here the joint variables are q1, q2. Okay, joint variables. Then the tau 1, tau 2 are supplied torques by the actuators. Tau 1 and tau 2 are the supplied torques, supplied or generated torques, supplied torques. Okay, supplied torques by the actuators, So similar to the polar arm, there are 3 stages. Okay, first step is A. What is A? We have to compute kinetic energy and potential energy. This is the first step. So kinetic energy and potential energy. So now here we have to compute for 2 links are there, 2 link masses are there. So the kinetic energy for link 1, okay, link 1, kinetic energy for link 1 is K1 equal to half M1 A1 square L1 square theta 1 dot square. Okay. Similarly, the potential energy for link 1 P1 equal to M1 G A1 sin theta 1. Okay. So this is equation number say equation number 1 and 2. Equation number 1 and 2. Then for link 2, similar to that, the kinetic energy and the potential energy for link 2. So for link 2, we have to use the forward kinematic equations. Forward kinematic equation for link 2. What is forward kinematics equation? X2 equal to A1 cos theta 1 plus A2 cos theta 1 plus theta 2. Okay, Y2 equal to A1 sin theta 1 plus A2 sin theta 1 plus theta 2. So now we differentiate this equation. Okay, so it becomes x2 dot equal to minus a1 sin theta 1 into theta 1 dot plus minus a2 theta 1 dot plus theta 2 dot sin theta 1 plus theta 2. Similarly, y2 dot equal to a1 theta 1 cos theta 1 plus a2. Here you see, here you can differentiate a2 theta 1 dot plus theta 2 dot into cos theta 1 plus theta 2. Clear? See here minus, here cos. Understand? So say equation number this is 1, 2. This is 3. This is 4. This is 5. So this is 6. Okay. So the velocity required, velocity is easily computed from this. So the velocity required for kinetic energy can be easily computed from these two relation. So velocity at the velocity of the joint 2 v2 square equal to x2 dot square plus y2 dot square, y2 dot square, right? So you just square these two terms and add. Okay, what we get? So we will be getting v2 square equal to a1 square theta 1 dot square plus a2 square theta 1 dot plus theta 2 dot the whole square plus 2a1 a2 c theta 1 dot square plus theta 1 dot and theta 2 dot cos theta 2. So square and adding. So squaring 5 square plus equation number 6 square will be getting this. You do it. Okay. Equation number, say this is equation number 7. So the kinetic energy of the joint 2, kinetic energy of the joint 2 is, or link, sorry, not joint, link, kinetic energy of the link. Kinetic energy of the link 2 is K2 equal to half M2 V2 square. So K2 equal to half M2 A1 square theta 1 dot square plus half M2 A2 square of theta 1 dot plus theta 2 dot the whole square. Okay, plus M2 A1 A2 theta 1 dot square plus theta 2 dots whole theta 1 and theta 2. Sorry. Okay, let us write here, then it will be clear. So this plus M2 A1 A2 theta 1 dot square plus theta 1 dot and theta 2 dot of cos theta 2, cos theta 2. So this is the kinetic energy equation. Similarly, the potential energy, this is potential energy, energy of the link 2, of the link 2 is P2 equal to M2 MGH, right? M2 G H is Y2, right? That is height. Say this from this figure. So height, this is this portion is x1. This is this at this point x1 y1. At this end, this end. So this is x2 comma y2. So this is the height. So height h is y2, right? So this is equation number 8 and 9. Equation number 8 and this is 9. Next one, first we have to compute. Say kinetic energy and potential energy. Next is we have to compute the B. Second step, B is Lagrangian equation. Lagrangian's equation. What is Lagrangian equation? L equal to K minus potential energy. That is kinetic energy minus potential energy. That is K1 plus K1 plus K2 minus P1 minus P2. So substitute the values from the relations, previous relations. We will be getting, actually, here we can substitute the P2, actually P2 equal to M2 G. What is Y2? Y2 is A1 sin theta 1 plus A2 sin theta 1 plus theta 2. Am I right? So this can be equation number 10. So by substituting the equations here, we will be getting the L term equal to Lagrangian equation equal to of M1 plus M2 A1 square theta 1 square plus of M2 A2 square theta 1 dot plus theta 2 dot whole square. Okay, theta 2 dot whole square. Okay, so next is plus this plus better you can write plus M2 A1 A2 theta 1 dot square plus theta 1 theta 2. Just substitute the previous relations here. Then cos theta 2 minus M1 plus M2 G A1 sin theta 1. Again minus M2 G A2 sin theta 1 plus theta 2. So this is the expression for a Lagrangian equation L. Okay. So now we have to compute dou L by dou theta 1. So dou L by dou theta 1 dot. Okay. So what we will get, just to differentiate that L equation with respect to theta 1 dot. So we will be getting M1 plus M2 of A1. You see, you differentiate this equation. So if you differentiate this, M1 plus M2, this theta 1 with respect to, we are differentiating with respect to theta 1. Okay. So these two will be here, 2 to cancel, right? So we are getting M1 plus M2 A1 square theta 1 dot, okay, plus M2 A2 square theta 1 dot plus theta 2 dot plus M2 A1 A2 twice theta 1 dot plus theta 2 dot cos theta 2. Okay, so this is dou L by dou theta. Now we have to differentiate this entire equation with respect to t. So we have to differentiate d by dt of dou L by dou theta dot 1. Okay, so if we differentiate with respect to t, we will be getting m1 plus m2 of a1 square theta 1 double dot plus m2 a2 square theta 1 double dot plus theta 2 double dot, okay, theta 2 double dot plus m2 a1 a2 2 theta 1 double dot plus theta 2 into cos theta 2 minus, okay, minus m2 a1 a2 2 theta 1 dot 2 theta 1 dot theta 2 dot theta 1 dot and theta 2 dot, okay, 2 theta 1 dot plus theta 1 dot square means sin theta 2, sin theta, understand? So this is dou t by d by dt of dou L by dou theta 1, okay, dou theta 1 dot. So this is the expression for first link. Okay. Next, we have to compute. Say if you simplify this, uh, dou L by dou theta 1, we found it. Then we have to find dou L by dou theta only. Okay, theta 1 only, because in the Lagrangian equation, so what is the formulation? Lagrangian formulation. Lagrangian formulation is dot. So the Lagrangian equation is d by dt of d by dt of dou L by dou theta 1 dot theta dot minus dou L by dou theta equal to tau. Okay, so this is the Lagrangian equation form. So we have to find dou L by dou theta 1. So dou L by dou theta 1, if you differentiate L expression, if you differentiate this equation L, okay, simply with respect to theta 1. So what we get? So we will be getting minus of m1 plus m2 g a1 cos theta 1 minus m2 g a2 cos of theta 1 plus theta 2. Okay, if you will similar to this, say this equation number, say equation number 10, 11. Okay, we can have this equation number 11. Equation number, this is equation number 12. This equation number 13. Okay, consider that. So next is similar to that. First we find dou L by dou theta 2 dot, dou theta 2 dot. So what do we get? M2, see, go to the L expression. So differentiate 11, this 11, equation number 11, with respect to theta 2. Okay, so what will get? M2 minus of m1 plus m2 g a1 cos theta 1 minus m2 g a2 cos of theta 1 plus theta 2. Okay, then dou L by dou theta 2. Okay, dou L by, sorry, this already we obtained, no? Sorry. Sorry. So dou L by dou theta 2 dot, dou L by dou theta 2 dot, this is equal to m2 a2 square of theta 1 dot plus theta 2 dot plus m2 a1 a2 theta 1 dot cos theta 2, right? So then d by dt of dou L by dou theta 2 dot. So what do you get? Do it, please. Tell me the answer. What I am getting is m2 a2 square theta 1 double dot plus theta 2 double dot m2 plus m2 a1 a2 theta 1 double dot cos theta 2 minus m2 a1 a2 theta 1 dot theta 2 dot sin theta 2, right? So equation number, so this equation number say 14, equation number 14, this equation number 15. Okay, so next we have to compute dou L by dou theta 2 only. So that is very simple. M2 A1 A2 theta 1 dot square plus theta 1 dot theta 2 dot sin theta 2 minus m2 a2 g m2 a2 g cos of theta 1 plus theta 2. Clear? This is finally according to the Lagrange's equation. What is the Lagrange's equation? Okay, so this is the Lagrangian equation. Clear? So Lagrangian equation, according to this solution, equation of motion, what we get is the two coupled nonlinear equation tau equal to m1 plus m2 a1 square plus m2 a2 square plus 2 m2 a1 a2 cos theta 2 cos theta 2. So theta cos theta 2 of theta 1 double dot. Clear? Plus m2 a2 square plus m2 a1 a2 cos theta 2 double dot minus m2 a1 a2 you get 2 theta 1 dot then theta 2 dot plus theta 2 dot square of sin theta 2 plus okay plus m1 m1 plus m2 of g a1 cos theta 1 plus m2 a2 m2 a2 g cos of theta 1 plus theta 2. So similarly tau, this is say tau 1, sorry, this is tau 2. So tau 2 equal to m2 a2 square plus m2 a1 a2 cos theta 2 theta 1 double dot plus m2 a2 square theta 2 double dot plus m2 a1 sorry m2 a1 a2 plus m2 a1 a2 theta 1 dot square sin theta 2 plus m2 ga2 cos of theta 1 plus theta 2. Clear? So now third part is, so second part is over. Third is C. What is C? Manipulator dynamics. Okay. Manipulator dynamics equation, right? So what is manipulator dynamics? M of q theta 1 double dot theta 2 double dot, clear, plus minus m2 a1 a2 to theta 1 dot theta 2 dot plus theta 2 dot square into sin theta 2. Next element is m2 a1 a2 theta 1 dot square sin theta 2. Just we rewrite in the convenient form from these relations. So these relations we separate like this. Okay. So plus m1 plus m2, sorry, m1 plus m2 g a1. You see here from this m1 plus m2 g a1 cos theta 1. This is a gravitational term. Okay, g cos theta 1 plus m2 g a2 cos of theta 1 plus theta 2. This is the gravitational vector. So next row is m2 g a2 cos of theta 1 plus theta 2. Okay. So equal to this, totally equal to tau 1 and tau 2. We rewrite, we have been rewriting the tau 1 tau 2 in the vector form, where okay, where m of q equal to, say, vector m1 plus m2 a1 square plus m2 a2 square, okay, plus 2 m2 a1 a2 cos theta 2. Next element is m2 a2 square. Just write the this component. So this first acceleration term. So the acceleration term components are, we are writing here, right? So that is m of, so cos theta 2. This element is m2 a2 square plus m2 a1 a2 cos theta 2. So this element is m2 a2 square plus m2 a1 a2 cos theta 2. Okay. So this is this element is m2 a2 square. That's all. This is the acceleration vector. Okay, m of q vector. Understand? So the manipulator dynamics, thus the manipulator dynamics standard form, you know, m of q double dot plus the Coriolis vector. Okay, So this is the inertia matrix. M of q is the inertia matrix. Inertia matrix. Okay, this is the Coriolis vector or centripetal force V of q comma q dot plus gravitational vector G of q equal to tau. So this is the standard form of the manipulator dynamic equation. So actually M of q here inertia matrix which is symmetric. So M of which is symmetric. Okay. So this is the standard manipulation vector. Actually, right? So with this, we conclude the two types of manipulator. We derived the manipulator dynamic relations using three steps. Okay. First step is finding kinetic energy and potential energy. Second step is to apply the Lagrangian equation. Third one is converting the equation into a vector form, in a standard vector form in this form. Okay, so totally three steps. Very easy to model these two manipulators. Okay, so thank you very much. We will discuss next class.